All right, chapter 10 review. Number 1, see what it wants us to do. A penny is dropped from a bridge into a pond. The distance the penny falls at 1/10 of a second intervals is given below. Compute the average speed from 0.2 to 0.4 seconds. It's kind of like that question on 24 there. Well, if I want to do the average speed, it's change in distance divided by change in time. And so if it's on the 0.4 to 0.2, let's see. At 0.4, we're at 2.56. Distance minus, back at 0.2, it was 0.64 distance. And our time, 0.4 minus 0.2. I'll do the bottom part, 0.2. I guess you can go ahead and just finish it all up. What do you get for the average speed during that time? How much? 9.6 feet per second. 9.6 feet per second. So this is the idea where we're looking for a rate of change, which is called the derivative in mathematics or calculus. Number 2, find the average rate of change for this function. Number 2, f of x equals 3x squared plus 5x. 3x squared plus 5x. Over the interval 0.9 to 1.1. This is really the exact same question, but they give us the equation this time and the values for x. So if I want the average rate, we're going to have to take our, get our two values. If I put 0.9 in, f of 0.9, I don't know, whatever you get when you substitute that in, I'll let you do that.
Um, 6.93.
6.93? 6.93. And if we put 1.1 in,
$9.13.
9.13? 9.13. So we're wanting a rate of change. We're wanting delta y over delta x again. So our change in y are our answers. Final minus initial, 9.13 minus 6.93. And our change in x's, 1.1 minus 0.9. How much? 11? Exactly 11? 11. There are no units with this, were there? No units with that. 11. Average rate of time change is 11. 11 per unit of x. Number 3, find the instantaneous rate of change. So these two, we're finding the average between 2 points. Instantaneous rate of change on a function. 7x plus 9, where x equals -2. Okay, so if I want to get instantaneously, we're going to use that formula for a derivative, that limit formula. Remember the limit formula, or you can look it up in the book. What limit formula can we use to find the instantaneous rate of change, or derivative it's called? Remember what it was? The limit as h approaches 0. F of x plus h minus f of x over h. Now, okay, yes. Now we have an x value that we can use. So when we do the limit of our function as h approaches 0, we can be putting our 2 in here, except when it's x plus h, it'll be 2 plus h, negative 2 plus h. So we are going to have negative 7 times negative 2 plus h plus 9. That's f of x plus h, minus f of x. So minus, I'm going to put brackets, 7 times negative 2 plus 9. So there's f of x plus h. X happens to be negative 2 in this case, so we can put a negative 2 where the x is. All divide. Oh, good question. Shouldn't be a negative 7. It's a positive 7. All divided by h. So we're just substituting into that limit formula that tells us the derivative, or the instantaneous rate of change, or the rate of change at that point. So let's do some simplifying now. The limit, as h approaches 0, that would be negative 14 plus 7h plus 9. Now I distribute a negative, negative 14, it'd be plus 14 minus 9, all over h. Let's see, our negative 14 and our positive 14, our positive 9 and our negative 9. 7! Those h's would cancel as well, wouldn't they? So this one's simplified. 7. We didn't even have to substitute a 0 in any h. Those h's all disappeared. So this one has an instantaneous rate of change, or slope, of positive 7 at x equals negative 2. Number 4. For the function f of x equals negative x squared, A, use the limit definition to find the slope of the function at x equals 1. Okay? Part A is just what we did. We're going to do it again. So we are going to find the limit of this function. So as what? At x equals 1. At x equals 1. So we're going to find the limit as h approaches 0 of negative, now x is 1, so I put a 1 plus h, quantity squared, minus f of x, negative x squared. So that's f of x plus h. Oh, I forgot to put my 1 in, didn't I? 1 squared. F of x plus h minus f of x, and x happens to equal 1. All divided by h. Limit as h approaches 0 of, okay, that's going to be a negative. We're going to have to square that out. It'll be 1 plus 2h plus h squared. 1 plus h times 1 plus h. Plus 1 minus a negative 1 squared, it'd be plus 1. All divided by h. So if I distributed that negative and simplified, let's see, what would we get? Negative 1 minus 2h minus h squared plus 1 all over h. That's when the negative 1 and the plus 1 are gone. And what can I do with the h? I can factor out an h. Limit as h approaches 0. If I factored out an h, I'm going to go ahead and leave it in the same order. Negative 2 minus h all over h. And now those h's are gone and we can substitute the 0 in. Negative 2 minus 0 is negative 2. That is the instantaneous rate of change, or the slope of that equation at x equals 1. Find the equation of the tangent line at x equals 1. Let's think a minute. I have some sort of an equation, negative x squared. Negative x squared is an equation, and this is what the thing looks like, negative x squared. at x equals -1. Right here was -1. And so we just figured out the slope of this line right here. Instantaneous rate of change is -2. That's what we just got. What do we need to know in order to write an equation of a line? What information do we need on the writing equation?
No, not a point.
I need to know a point. I already have the slope of it, so all I need is a point. I know the slope of this tangent line is -2. How am I going to get a point, which is that? How am I going to get the point?
They go across the x equals -1, so put -1 to the quadratic equation.
Put -1 into the function. Exactly right. I want to have -1 as my x, and f of -1 is my y, whatever the answer is. So we're going to do that. We're going to substitute -1 into the equation. -1 squared. What does that equal?
It's 1. 1. X equals 1.
-1. Square the -1 makes it positive, and there's a negative in front of it.
X equals 1 is the x 1. 1 is x equals 1.
Oh, I did the wrong thing. X equals 1 line. You're right. I've got it in the wrong spot. X equals 1. It's over here. So instead of this line, we'll just get rid of that. We wanted this line. X equals 1 I'm putting in. 1. And f of 1. Good thing Jackie was paying attention. F of 1. And that still gives us -1 there. 1 comma -1, but we needed to know the x was 1. So there we go. There's the information I need. Slope of the line and a point on the line. I can write the equation of a line. I'm going to use that point-slope form. Y minus our y value, which is -1, so it'd be y plus 1, equals m, our slope, -2, times x minus the x value, which is a 1. I'm just filling in point-slope form. Y plus 1 equals -2x plus 2. Subtract the 1. And we found the equation of that line right there. -2x plus 1. So it asks us a different question than we had seen before, but we have the knowledge to figure it out because we knew that that -2 was the slope of the line. And we can find a point on the line just by putting 1 into the original function. So we get a point on it. Number 5. Find the derivative of f of x equals 5x minus 8. So the derivative, how do we get the derivative of a function? Which is the instantaneous rate of change, which is the slope equation. Use the limit formula. That's what we've been doing, is finding the derivative. This limit formula finds us the derivative of it. So, in order to get it, I'm going to take the limit as h approaches 0 of f of x plus h. Now this time we don't know the x. So it'll be 5 times x plus h. I don't have a number to put in there. Minus 8. Minus f of x. And that in brackets. 5x minus h. Divided by h. This formula is that red formula right back here. That limit equation will find the derivative for us. That's what we're filling in. All right, so let's see. The limit as h, I keep wanting to say x, as h approaches 0. Distribute my 5x plus 5h minus 8. Distribute the negative, -5x plus 8 all over h. What cancels? 5x minus 5x, negative 8, plus 8, what else?
Only 5.
And then the x's actually go, and all I have left is 5. The derivative of that equation is 5. Now, let me give you a little connection here. Remember, the derivative gives us the slope of the equation? Tell me the slope of that equation. 5. But that's okay. That's the tie-in, though. Do you understand what you're finding? We're finding the slope of that equation. Well, the slope of that equation is just 5. Now, if it's an equation that's doing things like this, it's not one number. It varies. We'll have an equation that gives us the slope of something like that. Hopefully, we'll have an example like that soon. Number 6. For the function f of x equals, so they have a schizophrenic function, 3x plus 1 if x is less than or equal to, is that what that says? I think that's what that says, less than or equal to 17 minus x when the x's are greater than 4. So find the derivative of x at x equals 4 if it exists. And if it does not exist, explain why it does not exist. So remember what we do? We want to find the left-hand limit, and we want to find the right-hand limit, and we want to see if those two limits are the same. It's approaching the same thing. So I'm going to look at a little graph of it so we can figure out what's going on. So that first equation, well, that's a linear equation. Y-intercept 1, slope of 3. Y-intercept 1, slope of 3. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. And as long as I'm less than or equal to 4, we've got this going on, and we're including this point at 4. 4. That's what we're interested in, is what's happening when x is 4. 17 minus x. Oh, that one has a y-intercept of 17 right about here. Minus 1. Uh-oh. So if I go, what am I? 7 above, so if I go 1, 2, 3, 4, 5, 6, 7. I'm just trying to find another spot that's going to hit that line. This is the line that's going on. I wonder if those two things intersect. We're going to figure it out in just a minute. If they're really supposed to intersect or not. Because I'm just doing a hand sketch. And really, there is possibly an open circle right here. So what I'm going to... get rid of that dot. So what I'm going to do is just figure out when x really equals 4. If I put a 4 in this one, 3 times 4 is 12, plus 1 is 13. I get an answer of 13. 4 in that one, what's 17 minus 4? In other words, these things are exactly in the same spot. Right there. So tell me about it. Does the limit exist at 4?
Yes, it's equal.
Well, there's one problem. They are approaching the same thing. The left-hand limit is approaching 13. And the right-hand limit is approaching 13. Oh, they're asking for the limit, aren't they? Not the derivative. So our answer is yes. I was thinking derivative at that spot. Because we have a point, we wouldn't have a derivative at a point, a slope, a rate of change at a point. But that wasn't the question. The question was, oh, wait a minute. Read the question. Find the derivative. We are approaching the same thing, but do I have a derivative at that spot? Does not exist. Doesn't exist. There is no rate of change at a point. kind of review, because it makes a difference the question they ask. If they ask us for the limit, which I was thinking when I was doing this, there is a limit. Both of them approach 13. There is a limit answer. But there's not a derivative, which is a rate of change at 4, because it's a point. You might want to look back in the section. We looked at several examples when we don't have derivatives, and that was one of them, right at a point. Number 7. Position of an object. Oh, we'll go to the next page. The position of an object at time t is given by s of t equals 5 over t plus 3. Find the instantaneous velocity at t equals 3. What math are we going to do to get that answer? If we can substitute the 3 in, we can just substitute the 3 in. We're wanting to know, oh, wait a minute. No, velocity.
Oh.
This is just the position of it.
Oh.
What are we going to do to find the velocity?
Find the slope.
We want to find the slope of the equation there, which is the derivative of the equation there, and we have a limit formula to find the derivative. All we're doing is trying to find the derivative at s equals 3 of this equation. S derivative of 3. So we are going to take the limit as h approaches 0 of this function at x plus h, or t plus h in this case. We know t is 3. So we have 5 divided by t is 3. 3 plus h plus 3. I'm substituting the 3 plus h where the t is. Minus 5 over t is 3. 3 plus 3. All divided by h. Using the same formula again, the limit formula to find the derivative at that spot. So now we're just going to try to simplify this thing down to a point where I can actually substitute 0 where h is. Let's see, that's 5 over 6 plus h minus 5 over 6, all divided by h. So going to get a common denominator so that we can put those fractions in the numerator together. So the common denominator would be 6 times 6 plus h. Give myself a little more room so I'm not running into one above. So in that first equation, I'd have to multiply by 6 to get the new thing. 5 times 6 is 30. Minus, on the second one, I'd have to multiply by 6 plus h. 5 times 6 plus h. That's all over h. Just looking on a common denominator. So let's distribute that negative 5 on top. Limit as h approaches 0. We have 30 minus 30 minus 5h over 6 times 6 plus h, all divided by h. 30 minus 30 are all gone, aren't they? And instead of dividing by h, I'm going to multiply by 1 over h.
And the edge.
And so this h will cancel out with that h, won't it?
Edge.
Let me write my next line. The limit as h approaches 0, I just have negative 5 on top over 6 times 6 plus h. And if h is 0, I can now put a 0 there. 6 plus 0 is just 6. 6 times 6 is 36. Negative 5 over 36. That is the derivative for the instantaneous velocity. Negative 536 units per second, or whatever they were measuring. All right, so we had a whole bunch of derivative questions, different ways of asking that. We use that limit function to find our derivative. Number 8. New kind of question. For the function f of x equals negative a half x squared plus 4, draw the graph of f for x in the interval between negative 1 and 3. Draw shaded approximating rectangles for the left rectangle approximation method using 4 intervals. So we're supposed to draw it out, and then we're going to compute that left rectangular approximation method to figure out the area there. And this is called the integral, the definite integral. No, they didn't call it an integral on this. That's what we're trying to do here. F of x, negative a half x squared plus 4. So they're wanting us to graph this, and they only want the graph between what x values?
From negative 1.
Negative 1 to 3. So between negative 1 and 3. So between negative 1 and positive 3, that's all we want to graph this at. So I'm going to go ahead and get the exact values at negative 1. F of negative 1, so I know exactly where it is. Negative 1 squared is 1, so it's negative a half plus 4, that's 3.5. Did I do it right? 3.5. And then 0, f of 0. Substitute a 0 in, you get 4. So it's at 4 there. Then 1, put a 1 in. And it's exactly the same thing, 3.5. Then f of 2, 4, negative 2 plus 4, 2. And finally, put a 3 in. 9, what's that? Negative 4.5 plus 4, 1/2? Negative a half, isn't it? Negative a half. Negative a half. So this is the graph of the parabola that we're trying to find the area here. And they said, after we draw this out, do shaded rectangle, or do rectangles with the left rectangular approximation, which means the left side is the height of our rectangle. So there's one. Left side. There's another one. There's another one. And there's another one just to the x-axis down there. So we know we have some extra stuff and left out stuff, but we're just trying to approximate it. So we need to find the area. How wide are each of these rectangles? And there are 4 of them. 1, 2, 3, 4.
1.
They're all just 1 wide, and so finding the area, it's going to be 1 times the height. Well, there's the height. So 1 times all those numbers, add, oh, wait a minute. Sorry. 1, 2, 3, 4. 1, 2, 3, 4. Not the last one. X. Don't use the last one. That's not one of the rectangles. So all we need to do is find the sum of those 4. If I added correctly, 13. Those would be the sum of those rectangles. So our estimation for the area under this curve is 13. That'll be approximately that. That's part B, I guess. Part B is 13. Part A was doing all this stuff. And the graph. Number 9. Estimate how you can find the area under the graph of the function 3x plus 5. F of x equals 3x plus 5. From x equals 0 to 2 by looking at the graph and using mental computation only. Well, let's do a little sketch then. That 3x plus 5 is a line, right? Y-intercept 5, slope of 3, so let's say it looks something like this. I have this line coming along. And we are wanting to find the area under that graph between 0 and 2. So here's 0, 1, 2, there's 2, between 0 and 2. You're trying to find this area. What concept do we use to find that area? What's that? Is it a shape we know?
Yeah.
All we would do is find the area of that trapezoid. Here's your answer. It's the area of a trapezoid. Now, they didn't ask us to actually do it. If they ask us to actually do it, remember the area of a trapezoid is 1/2 height times base 1 plus base 2. And we could do this real easy in case they ask. The height of it is the length between the bases, 2. And one base, well, how tall is this first base? 5. Plus, and how would I get the height of the second one? Substitute x equals 2. 3 times 2 is 6 plus 5? 11. Half of 2 is 1. 5 plus 11 is 16. That happens to be the area under the curve. They didn't ask. Number 10. Use the graph to find the limits if they exist. All right, they graphed it all out for us already here. So they want 10 part A. What is the limit of this function as x approaches 2 from the right? You see that little plus sign there. What's that limit?
4.
Be careful with the scale, which happens to be by ones. So it's 3. It approaches 3. The limit of that function as x approaches 2 from the left. 1. The height of that thing, or the value of it, is at 1. See? So what would be the limit of that function as x approaches 2? Does not exist. Does not exist. Because it's approaching 3 from the right, 1 from the left. It's not the same left and right hand limit. The limit does not exist. Number 11. Assume the limit of the function equals 5 when x approaches negative 3. Oh, the limit of f is 5 when x approaches negative 3. And the limit of g is 7 when x approaches negative 3. So what would I do to find the limit of the function f divided by the function g squared as x approaches negative 3? This is using the rules of limits that says, oh, this is equal to just finding the limit of the function f as x approaches negative 3 divided by the limit of the function g as x approaches negative 3 squared. Our property says we can just do this. So what was the limit of the function f as x approached negative 3? 5. What was the limit of the function g as x approached negative 3? 7, which is supposed to be squared. 5/49. There's our answer. Number 12. Find the limit of this function as x approaches 5 if it exists. So I'm going to try to get a little sketch of a graph again. This one. That equals x squared minus 3 when the x's are less than 5. And it equals 4x plus 2 when the x's are greater than or equal to 5. So I'm going to go ahead and do at 5 just to see what number we get on both of these. If I do 5 on the top one, 5 squared is 25 minus 3 gives me what number? It goes to 22. And this last one, 4 times 5 is 20 plus 2. Oh, it also goes to 22, huh? Now, this first one is a parabola, x squared minus 3. It's a parabola. What is it? When x's are less than 5. That. 22. That's the left. That's the top graph. And 4x plus 2 is a line, but it also is at that same spot. It's a line. It's doing this. But it fills it in because we can be equal to 5 on that one. So what's the limit? Are they asking for the limit? Yeah. What's the limit of this function? 22. Both of them are approaching that same value, 22. Number 13. For the function f of x equals 3 sine x over x, find the limit of this function as x approaches infinity. Well, we better look at that graph. Probably don't graph that one by hand very well. 3 sine x over x. Y equals 3, oh, I need parentheses, 3 sine x divided by x. Mode, I'm in radians, that all looks good. Zoom trig, choice number 7. Need to make that a little wider, don't we? Window, minimum, let's go negative 25. Maximum, positive 25. That's not quite to infinity, but I think it'll be enough where we can figure out what's happening. What is this thing approaching as our x's go to infinity? 0. It's approaching 0. As we head to infinity, 0. And what's part B? Is it heads to negative infinity? It's 0 as well. As x is heading to negative infinity, it's heading to 0. So we just look at the graph and we can tell the limit where it is heading. 14. 14. Find the limit of x squared plus 16 over x minus 4 as x approaches 4. Well, we know we can't just substitute the 4 in because it'd be dividing by 0. And we can't factor that x squared plus 16 and cancel anything out. Too bad it's not x squared minus 16. So again, we are just going to look at a graph. Where did my graph calculator go? So y equals, what is it, x squared plus 16? X squared plus 16 divided by x minus 4. We'll do a standard window, see if it shows up. Not very much of it showed up, did it? So let's make that window a little bigger. Let's make those x's. I think it's probably the y's that I need. Y max 20. Let me see if that does enough. Barely starting to pick it up in my top right corner. Window Y max 30. All right, we know we have our vertical asymptote there at 4. We know it can't equal that. So we know at 1, 2, 3, 4, we've got our vertical asymptote coming here. So this thing is heading down there, it's heading up there. So what is the limit as this function is approaching 4? If we approach it from the left, if we approach it from the right, what happens? To the left, it's to negative infinity, and from the right, it's to positive infinity. So the limit does not exist because they're approaching two different things. One is heading down over here to negative infinity. The right side is heading up to positive infinity. The limit does not exist. So don't be afraid of that answer if that's the right answer. There isn't one. 15. Use a calculator to find the right rectangular approximation method area approximation for the area under the graph. Does everybody have their calculator programmed? If not, I'll help you get it programmed. Let's see my calculator here. And what you need to do is you need to enter this equation in the y sub 1 spot. So 3x squared minus 4x plus 1. I have to have that equation in the y sub 1. Program right rectangular. A, it says from x equals 0, A is 0, to x equals 4, B is 4, with 10 approximating rectangles, N is 10, try 10 again, N is 10. That should be your answer. If you need help with that program, now's the time. I'm going to stop the recording here.